Hey guys, today we're going to take our previous knowledge about equations of planes and extend those so that we can find the scalar equation of a plane. So firstly, we're going to try this warm-up. I want you to see if you can find the vector equation of the plane containing the line with this equation and the point 513. So if you're watching the video, just take a second and pause, and then we'll come back and do it together. So now that you've taken a second to try this on your own, we're going to do it together. So we have a line that is inside of our plane and a point that we know is on the plane. Now, in order to find the vector equation of a plane, we need two direction vectors and a vector that goes from the origin out to a point on the plane. So I have one direction vector already contained inside my line, and that is the point 3, or the vector, I should say, 3, negative 8, 7. And so I'm going to use that as my first direction vector. Now, my second direction vector isn't super visible right now, but I do know that this is a point, which, well, it's a vector that connects 0, 0, 0 to a point on this line. So I can simply, let's say we call this point number 1. I can use 2, negative 9, 10 as point number 1, and then we have a point number 2, which is 5, 1, 3. And in order to find a direction vector, I can simply find let's say the vector that connects point 1 to point 2. So I'm going to take point 2 components, which are the tip of the vector components, and minus the tail components. So we'll do 5 minus 2 to get 3, 1 minus negative 9 to get 10, and 3 minus 10 to get negative 7. So that will be our second direction vector. And for our third vector that goes from 0, 0, 0 out to a point on the plane, you can use point 1 or point 2 as that vector. So our plane, which we often use pi to kind of represent a plane, and then we'll use L to represent a line, can be expressed like this. So we have a direction vector that goes from the origin out to a point. You could have also used 5, 1, 3 for this. And then we have two direction vectors that are non-collinear vectors. So they're not the same vector. And we need to multiply them by parameters s and t to represent and generate all the possible points that could be on this plane. So there's your solution. Okay, so let's take what we know and we're going to extend this so that we can find the scalar equation of a plane. Now this looks somewhat similar to the scalar equation of a line in 2 space, but basically we have this z component here for the scalar equation of a plane in 3 space, and it will be plus some constant d. So a, b, c in this case represents a normal vector to the plane, and we use this normal as our a, b, and c coefficients so that any point that we plug in and add to the d value will actually result in 0. Now the normal kind of acts as a handle to the plane, and that's why the scalar equation can simply use a normal and it will still be a unique plane, whereas when we look at the vector equation, we need 2 direction vectors. So why is it that one normal can uniquely define a plane with this d value, of course? So I want to show you that. All right, guys, so I've got my plane here and I have a normal vector. And like I said, the normal vector kind of acts like a handle to our plane. So if we imagine that this plane is defined in space by this normal vector, wherever I turn the normal vector, my plane will also turn. And that's why we can use a normal vector to uniquely define a plane in space. Now, the only thing that we also need is a point, because if I have this normal vector, how do I know where in space my plane actually stops? I know the orientation of my plane, but I don't know where in space it stops. So by having a point there as well, And I have that normal vector that tells me the orientation, and the point tells me, oh, if I have a point up here, that's where my plane needs to stop in space. And that's kind of the idea of the scalar equation of our plane. Okay, so let's take a look at an example here. We're going to determine the scalar equation of the plane that contains the normal vector 3, negative 2, 5, and contains the point 1, 2, negative 3. So this is pretty straightforward. We simply want to plug in A, B, and C as the components of our normal vector, and then we'll plug in the point to solve for D. So here's what we've got so far. Oh, that should be negative 2. And then I'm simply going to plug in 1, 2, and negative 3 in for x, y, and z. And then we'll solve for D. So this is going to give us 3 minus 4 minus 15 plus D. And don't forget always that some people want to just jump to the next step and have D right away. And I have a lot of students that will take this value and they'll say, okay, negative 4 and negative 15, that's negative 19 and 3. So D must be negative 16. But really what we have over here is 16 plus D. And that means that D actually equals positive 16. So just remember that. That's a big mistake that I see along the way. And then we're just going to take that D value and sub it back into that second line that we have up there. So this is what your equation should read. And if you want to check your answer, you could always plug this point back in for X, Y, and Z and just make sure that you get 16 or negative 16 plus 16, so 0 equals 0. Make sure you get a true statement. We can also use the dot product with the normal and the point to solve for the D value, but I personally feel that this way is kind of the easiest way to solve for D. So we'll kind of go with this method. Okay, so a couple follow-up questions. Is the vector A parallel to our plane? Now, if we think about this, I have a plane in space. Let's just say that's my plane, and I have a normal, and that normal is the vector 3, negative 2, 5. Now, if I have another vector that's parallel to my plane, let's say, that means that the vector that's parallel to my plane is actually perpendicular to the normal here, right? If I move this down and we kind of connect these two guys here, then these two things must be meeting at a 90-degree angle if that direction vector or the vector is parallel to my plane. So how can we check if two vectors are perpendicular? Well, I can check if two vectors are perpendicular simply by testing if the dot product is equal to 0. So here's what I'm going to do. I'm going to see if n dot A ends up equaling 0. So we'll take the vector 3, negative 2, 5 and dot it with 4, 1, negative 2. Okay, so remember your dot product is the products of each similar component. So the x's, the y's, the z's, and then we add them together. So here I'm seeing that we have 12 plus negative 2 plus negative 10, and that actually gives us 0. And that tells me that the normal and my vector A are in fact perpendicular, making that vector A actually parallel to my plane. So therefore A is in fact parallel to the plane. Is vector B 15, negative 10, 25 normal to the plane? Now, we know that there are basically there's a unique normal to my plane. I could technically have its opposite vector, which could also be normal to the plane, depending on which way it's kind of coming out from the plane, the top or the bottom. Anything else should basically just be basically a collinear vector to my normal vector. So if my normal vector is 3, negative 2, 5, then I would need my normal vector to be some multiple that gives me, to have some scalar multiple that gives me vector B. So is there any multiple that I can multiply my normal vector by to give me vector b here. Now we can solve for this similar to how we did in Unit 2. So if you're really unsure and it's not an easy, like, oh yeah, I can just multiply everything by 2. If it's not easy, you can set up 3 unique equations and solve for k with each x, y, z component. But I think we can see here that, oh, let me just double check this normal. Oh yeah, okay, we're good. I think we can kind of see here that if I take each of these components and I multiply each of these by 5, I actually get 15, -10, and 25. So this makes k, if k is equal to 5, then these are scalar multiples of one another, and that means that the normals are collinear. So 15, -10, 25 would also be another option for a normal to the plane. All right, let's try another example here. Find the scalar equation of the plane containing the points A, B, and C. Okay, so I need to find a normal to the plane, and if we think about 3 points, 3 points uniquely define a plane in space, because if I plot those 3 points, a flat surface would kind of lie over them. So let me show you what I mean. All right, so you can see over in the legend here that I've graphed our 3 points in space. And with GeoGebra, we can actually create a plane really easily by simply clicking those 3 points that we want to define our plane. And then we can see here that just with those that basic tool there, that this kind of defines that plane that covers all those 3 points. Now, if I only had 2 of them, the plane would kind of wobble on those 2. But as soon as I add in a third, it stabilizes the plane, and that uniquely defines the plane in space. Now, if I can find 2 direction vectors, or 2 vectors that essentially connect these sets of points here, I should be able to cross them and get the normal of the plane. So let's hop back over here, and we're just going to find 2 vectors. It can be any 2 vectors. So let's say we do AB and AC, for instance. Okay, so remember we want to do tip components minus tail components, so we'll do 4 minus -3, that gives us 7, 6 minus -1, and 2 minus -2. So there's our vector AB, here's AC. So tip components minus tail components, C minus A, gives us 8, -3, and 3. Okay, so we're going to take these guys, we're going to cross them, and that should give us a normal to our plane. So, oops. All right, so remember with cross product, if I want to do, let's say, AB crossed with AC, I'm going to write AB out twice, one after the other. And then write AC out twice, one after the other. And then I can basically just erase or cross out these first 2 sections there. We don't actually really need those, but just to give you a visual of kind of what we want to do. And then we're going to take the multiples going down from, so top left to bottom right, minus the product going from top right to bottom left. So for the first one, we'll do 7 times 3. That will give us 21. And we'll subtract 4 times -3. That gives us minus -12. For the second one, we'll do 4 times 8, gives us 32, minus 7 times 3, gives us 21. And then finally, 7 times -3, minus 7 times 8. Okay, I'm going slow just as a reminder from last unit for this one, but we'll go faster once we do some other ones. And when we simplify here, we should end up getting 33, 11, -77. Now, what we like to do with normals is express normals kind of in simplest terms in a sense. And what I mean by that is basically if you can see that your x, y, and z coordinate of this vector, or component of this vector, I should say, can be divisible by the same amount. We typically do that, and we'll always aim as well to have x as a positive. So if you happen to have, like, maybe you cross the vectors in the opposite direction and you got -33, -11, 77, let's just divide out a -11 so that we can make that x component positive. Usually like to have the first component or the first coefficient of the scalar equation of a plane positive, just so we're all expressing that in a similar way. So mine's already positive, so I'm actually going to take each component here and divide by 11. So we'll get 3, 1, and -7. This is basically just a vector that's a collinear vector to the one that we just found. So it works as a normal as well, and it just makes our lives a little bit easier when we're doing the next calculation. Okay, so here's what I know right now. We have 3x plus 1y minus 7z plus some value of d, which equals 0. Now all you need to do is plug in a point on the plane in order to solve for d. So I'm going to plug in a. We'll plug in -3, -1, -2. Okay, you can choose any one of those 3 points, and if you want to choose a different one and see if you get the same answer, go for it. Okay, so we're plugging this in here. We're getting -9 minus 1, that gives us -10, plus 14, that gives us 4. And don't forget that moving the 4 to the other side gives us -4. So you're simply going to plug that in for your d value. And you will also notice again that my leading coefficient here, I don't know if I can call it leading coefficient, but the first coefficient in front of x here is positive. And you'll notice that the equation of the plane is fully reduced, meaning that each coefficient here does not have any like common multiple that could be common factored out. Now, if I left it as 33, 11, -77, you would notice that you would probably get like -44 here, and then you would want to reduce that and divide out the common factor of 11 in order to get your scalar equation kind of in simplest terms or simplest form. Okay, the nice thing about the scalar equation, and the reason we like scalar equation of a plane, is because it gives us kind of a similar way that we can express an equation of a plane, because there's many different equations that can be generated when we do vector equations of planes. All right, so you can see here that I've graphed our vector AB and our vector AC. So you can actually see them sitting inside the graph here. And our normal vector, I'm going to call this vector n for normal, we ended up getting as 3, 1, -7. And you can kind of see here, like if we take a look at that from a bunch of different angles here, you can see that this is perpendicular to our plane. And I would have got that no matter which way I chose to do these vectors and cross them. If I crossed them the other way and I got -3, -1, 7, you would have just had a normal coming out the other side of the plane, right? It would have been like sticking up this way. So both of those work, but we do want to try to keep it positive if possible, or that first coordinate positive if possible. So there's our plane, and you can actually see when I clicked on those 3 points, it actually created the equation of my plane for me here. So you can use that to check your work if you're working in GeoGebra. All right, let's try another example here. We're going to determine the scalar equation of a couple planes here. So we want something parallel to the xz plane and through the point -7, 8, 9. Okay, so the xz plane. So if we draw our coordinate system here, we know this is x, y, z. So the xz plane is kind of the plane that's flat along the x and z axes here. So there's our plane. So we want our plane to be parallel to this, which means that they could share a normal, and we want it to be through a specific point. So I don't really know, like imagine that this plane can kind of go really anywhere left and right in space right now. Now the point actually stops it and defines it at a particular area in space. So here's what I want to find. If I can find two direction vectors on the xz plane and cross them, I should get a normal. But I actually don't really even need to do the calculation for this. I know that there's one specific vector that's definitely perpendicular to that xy or that xz plane, and that's this vector right here. The vector that comes straight out from those two direction vectors at a 90-degree angle to both of them. And that happens to be the vector, the unit vector in the y direction, which is j hat. So if I crossed I hat and k hat, I would actually get j hat, the unit vector in the y direction. So we can actually use j hat as our normal vector. So if this picture is not quite doing it for you, I'm going to show you on GeoGebra here. All right, so here we have the xz plane. So you can kind of see that it's flat, it covers the z and x axis, and then we know that the x, y, and z axes all meet each other at a right angle. So you can see here that I have graphed the unit vector in the x direction, which we call I hat, or the vector I, and the unit vector in the z direction. Now I've also graphed here, you can see the unit vector in the y direction, and this is perpendicular no matter how we kind of look at it here from whatever angle. This is going to be perpendicular to our plane. So we should be able to use this as our normal vector. Now our plane also has a specific point. So we kind of need to see where to move this plane in space so that it actually contains that point. So let's hop back over here. So here's our normal vector. It's going to be 0, 1, 0. And we're going to calculate what we need to get it through the point -7, 8, 9 by solving for d. All right, so really what we have here is y plus d equals 0. Z and x kind of get canceled out because they have coefficients of 0. So really, when we plug in our point here, we get 8 for y, and that makes d -8. So plugging this back into our original equation, we're just going to have y minus 8 equals 0. So I will show you that plane over here on GeoGebra. Got to zoom out just a little bit here to see this. All right, so there's our plane right there. So you can see that those two planes are parallel, which means they can share a normal. And this specific plane right here is going to have that point that we need. Let's try another one here. So we want our plane to contain the line 1, 2, with position vector 1, 2, 4 and direction vector 4, 1, 11. And we want it to be perpendicular to our second line here. Okay, so if it contains the line, it contains the direction vector. It also contains the point that goes out to, that our position vector goes out to. And if it's perpendicular to this other line, that means we should be able to use the direction vector of this other line as the normal to our plane. So I have a normal now. It's 2, 3, -1. And I can use the point on my first line as a point on my new plane, because I know that line lies inside of the plane that I'm looking for. So you're just going to set up your equation here. And we're going to plug in the point to solve for for d. All right, so it looks like I'm getting 4. And that means d equals -4. So you're going to sub that back in. Okay, and if you are a little bit confused by what I just did, I'll show you a visual on GeoGebra as well. All right, so I've graphed our two lines in space. The first line is this guy, and he is inside the plane, which means that the point A, which I've marked off here, is actually inside the plane as well. Now this guy is going to be normal to the plane. So once we find our plane, we should expect that our vector y meets the plane at a perpendicular angle, and the plane also needs to cut through this point A, and it has a direction vector inside. So I'm expecting the plane to kind of cut through right here so that it's perpendicular to this line y. So let's take a look at our plane graph here. All right, and there you can see it. So you can see it cutting through that line at point A, which means that it shares that direction vector inside, and then the other line, our second line, is normal to that vector. So the direction vector on line y is actually our normal vector to our plane.